All right, we have sort of a back to return of the usual sort of ideas. I just posted a video on talking about quantum hype, and somehow that somehow all the non-technical videos I make always become extremely popular, and the technical ones do not. Read into that how you will, but I just saw, just a few hours after I uploaded a video, it's already sitting at hundreds of views, which, okay, that's not objectively a lot of views, but relative to the usual trend of things, that's a lot. So I don't know what it is with the search algorithm or whatnot, but that's certainly going up there. Um, yeah. So anyway, we'll get back to a more technical content now after that quick diversion. And what we're going to be talking about now is this recent paper. Well, we're going to be implementing it mostly. This is, as you can see from the sidebar here, just like a month ago, September, October. Yeah, got to make sure I get my months right. October 2022, so this year, 2022, for anyone who just woke up from a coma. And so, as you can see, it's a very enticing, title. Noise can be helpful for variational quantum algorithms. Well, that seems really, really nice because, as it turns out, we happen to have a lot of noise in our quantum devices. So, we want all that we can get. Um, so basically, the first thing to say is that it's a really short paper. If I scroll through, you can see that this whole page is like definitions right here, and then one theorem, and then some results, and then it's done. So it's really short, but all it's saying is basically that the noise present in certain types of noise can be beneficial in certain situations. It's not, the title is more enticing than the true result. But basically, if you remember that uh, there are certain, when you're optimizing, right, noisy variational algorithm, there's multiple types of noise. So you have shots that you have to take, right? You're approximating some value, and you're always going to have a finite number of shots. And so that's a source of noise. You're also going to potentially have, random perturbations, basically inexact, right? If you're sending a pulse or you're moving your ion, right? You're never going to do it perfectly because things don't work perfectly in the real world. And so you're going to have some, perturbations, and it's going to be slightly, disturbed. And so stuff like that um, can be noise inducing. And so there's noise there. Um, it's important to note that right off the bat, as they say here, that they do not mean general noise, which is CPTP, is what you often see, completely positive and trace preserving. Of course, trace preserving, very important. So that's not general. Like, noise as defined in a extremely general quantum sense is not beneficial. In fact, there is noise-induced Barium plateaus, which is a different kind of Barium plateaus, rather than if you think of like the gradients becoming flatter and flatter. As so you have like your minimum, and then the gradients around that become flatter and flatter. As normal Barium plateaus, the entire regime becomes flatter in noise-induced Barium plateaus. I don't think I've made a video on noise-induced Barium plateaus. I know that was on my to-do list. I think I was having a really hard time replicating the results, but that might be something we'll talk about eventually. So just specific kinds of noise, such as shot noise, and also somewhere, for example, yeah, as I say here, measurements, fluctuations, depolarizing noises are covered. So this sort of stuff, not generic quantum interactions. So it's important to preface that. So that does not mean that if you have a fault tolerant quantum computer and you have a noisy quantum computer, that you're necessarily going to want to use a noisy quantum computer to do optimization. That's not what they're saying here. It's just saying that these certain types of noise can be useful. And the way to think of them as useful is in a very specific context. And they're looking specifically for saddle points. And so saddle points are basically, you probably if you've ever taken like a calculus class, you'll probably have heard of this. They're points on a function in which the gradient is 0, but are not a local optima or minima, or not a minima, I should say, or maxima. So the way, right, you find critical points is a common like problem, right, in calculus is you say, okay, I want to find the critical points of this function. So you take the derivative and you set it equal to 0, and you solve and you say, okay, let's, for example, take x squared, right? You say, okay, well, what's the critical point? You say, okay, the derivative of x squared is 2x, right? So the derivative of x squared is 2x. And so you say, okay, set that equal to 0. That's equal to 0 when x is equal to 0. So that's our critical point. And you want to say, is this a minimum or a maximum? And one way to do that is the first derivative test. Sorry, I had to pause the video there, so it's sort of disjoint right now in my mind. But so we're talking about derivatives. Derivative of x squared is 2x, set equal to 0. We have x equals 0. That's our critical point. How do we determine if it's a minimum or a maximum? Well, at the minimum, if f prime of x changes from negative to positive, which of course it does, below 0, it's obviously negative since it's just a linear function. Above 0 is positive, so it's a minimum, which of course is obvious. We can see that saddle points can be determined if both sides are positive or both sides are negative. They can also be determined using the second derivative test, which is often done. You can look at the this is often done in optimization. You'll often see people talk about the Hessian. And so, you can do this too for a single one. If f double prime is positive and f double prime is negative, that's a minimum or a maximum. If f double prime, or obviously the second derivative, is 0, then it's a saddle point. And this is also true of the Hessian, which is the matrix of second derivatives for a function of multiple variables. If that function is, or if that matrix is indefinite, then there's a saddle point at that critical point. And so that's basically what it means. And so if you look at the example, it does a pretty good job of showing, right? You can see you take the gradient, it's like at that instantaneous moment, it's flat. You can't escape it because the gradient is 0 at that point. But it's not a minimum, right? You would really want to get down either of these. And so that's a lot of why, there's a lot of theories too. I'm not up to date on the stochastic gradient descent theories about like your true gradient descent versus stochastic, you'll like weave your way, but there's a lot of stuff going on there. But basically what this is saying is like, okay, if we reach this point, we're not going to actually get the true gradient. We're going to get a little plus or minus, and so that's going to nudge us off the saddle point and knock us down. So it can be helpful in these situations. And so the strict saddle points, that's just a subset of saddle points. So they can say in this situation, it is useful. Now that's a very specific situation that we don't even know how common, like saddle points. There are times in which we have vanishing gradient problems in classical and quantum machine learning, but whether or not that's a result of saddle points or other problems, I don't know if that's known. So how useful this is, I can't say, but it's a very interesting idea in the sense that, okay, lots of definitions here. What I want to say is, right here, right, this is what we're really doing is, okay, we have our gradient descent algorithm right here, but what we're really doing is we're doing a gradient descent algorithm plus some noise, right? This is going to perturb us basically. So it's like adding random noise, sort of, that perturbs our gradient, which makes us sort of avoid certain points. So the example they do is we have a unitary of x rotations and 2 strongly entangling layers. You can see right here. And the Hamiltonian operator is the sum of the z operators. So of course the minimum is going to be -4 for 4 qubits because it's the sum, not the multiplication. So we can see here that there are different noise levels, and we can see how it helps. You can see at certain levels of noise. Worth noting before I jump into our results that this is from manually added Gaussian distributions. They did extensive, they found initial parameters so that the gradient descent in a noiseless case converges to a strict saddle point. I did not do extensive parameter serving to check if the saddle point. Taking the Hessian and TensorFlow Quantum is actually a big problem right now. I know it's been in there for a while, so I don't even want to deal with doing that. But the interesting result is, they said extensive parameter searching to sort of get this to be the case. I did not have to do extensive. I did 0 parameter searching for mine, and we'll still get some cool results. So they also show, just some more initial conditions. This is just another one. This is for VQE instead of, this is a different Hamiltonian, but pretty much the same setup, and showing that noisy, even for hydrogen atom or hydrogen molecule VQEs, can be helpful. And this is an example of, the real hardware, right? Where this is real hardware doesn't have perfect noise. Real hardware has really, I guess real hardware has the exact noise that real hardware has, but it's not perfectly Gaussian noise. So yeah, this is, I think this is interesting work. Obviously, this is a quick overview of it, but we're going to be looking at not this result, but just sort of this section here. Although that VQE result is pretty interesting. And the future work, they recommend talking about metropolis sampling to avoid rugged landscapes. There's lots of interesting things. There's a paper I saw on, like, it's called Monte Carlo VQA or something, but we might talk about that later. So I think there's a lot of cool ideas here, and how we can fully exploit what is sort of considered a limitation, right? Our inexact approximation of the gradient. Maybe we can make it a benefit. So let's get into an actual implementation. We have TensorFlow, TensorFlow Quantum, all the standard stuff. So now we're just writing. This was thankfully, and part of the reason I chose this paper, if I'm being candid, very easy to implement. So we have our model that we want to optimize. It's just very plain. We do 400 iterations, same as in the paper. I'm just doing Atom. I don't know if that's exactly what they did, but it's good enough. We take the gradient to minimize the predictions. We get the output, and we optimize that loop. Pretty straightforward. To make the circuit, we have however many layers, however many qubits. We do single rotations of Rx gates followed by strongly entangling gates, which is the just basically circular C-naughts. And then we have to make our actual model. So we define our qubits, which is just however many we want. We generate our circuit. Our operation this time is the sum of these Z operators. We initialize it here. I'm going to compare 2 results. I compared the default initialization, which is simply a random picking from 0 to 2 pi, and I compared zeros. So in the random one, they're obviously, the noises are all initialized to different random initializations. And 0, they're all initialized to 0. And so we'll look at both of them. We'll look at the zeros first and then random initialization. We can see if we have noise, what I'm doing here is just adding depolarizing noise at the appropriate level. We obviously need to use a noisy PQC instead. We use 1024 samples. For the noiseless case, we're doing no samples for speedy adjoint differentiation. Boy, I tell you, you get used to adjoint differentiation, you never want to go back to parameter shift because it's so slow. Even for 4 qubits, I forget, I do so much adjoint. I'm like, I forget that. Oh my gosh, it's so slow doing parameter shift. But anyway, we create the model. This is obviously like the most simple TFQ model you could do. You have your default string type input, you put it into the PQC, and you get the output. We specify our noise levels, the same as in the paper. Our results, how many qubits we're doing 4 and 2, just like that first set of results. We make our model, we optimize it, and we get the result history. This first results we're looking at is from the 0 initialized one. We can see, surprisingly, that 0 initialized, I guess, is very hard to get out of for whatever reason. So we can see different noise levels. We can see that zero noise is actually really bad, surprisingly or not surprisingly. Some noise, a little bit of noise right here, you can see that's the noise level is really good. not that good because -4 is the optimum. A little more noise helps at first, but isn't good. And then 1 and 2, you're basically unable to determine anything from the expected value. It's just, garbage that you're getting. So now let's look at the random. So this is just picking a random point. This is more realistic probably to how people would act. We can see that the high noise levels, again, just iterate around 0, because what we're probably seeing here is that the noise is simply too high. There's nothing that the circuit can determine from it. We can see here that 0, once again, noise is very smooth, but it converges to only -2. A little noise up above, which was the best, converges to the exact same point, but a little faster. And here we can see even a higher noise level is actually the best one down here, converging to -3. So we can see some interesting results. Pretty cool graphs. We can see that noise can in fact help even without extensive searching, which is very interesting. This is literally the first run I did. I was like, oh, code worked. That's very cool. And yeah, so it's interesting to see that. I don't know if there's a saddle point here. I encourage you, check out the code, look at the Hessian, see is it definite or not, and maybe this is a saddle point. I don't know, but even if it's not, it's cool to see that certain types of noise might be able to help even in different scenarios. And I wonder, now this is just a big speculation, I wonder though, in the future, if we're like, hey, this is a local convergence, let's tune down our error correction and actually allow some noise. I wonder what that would look like. But I don't know if that's actually going to happen. So this is really blitz. I know I'm speeding through it, but I just want to get it out. It's pretty straightforward paper, pretty cool. I like the results. I just want to get this out because I was like, wow, the previous video is blowing up. Maybe today is just a popular day to be watching YouTube or something. And I figured, I said I would get it out, and so here it is, So anyway, I have some more videos planned. As I mentioned in the previous one, there's a cool NISC video I want to talk about. There's another intro to quantum mechanics video. There's some more TFQ videos, some more open QAOA videos. So lots of stuff. Of course, I say that every video, and I take forever to make them. But anyway, that's all for now.